Hello students, welcome back. We just had a review and let's go over to section 1. But before that, we need just a little bit more review. A brief review, a review of review. What am I talking about? I'm talking about this. The definition of the linear map. Now, do you see the parallel between the definition of the linear maps and the conditions for subspaces? Preserves the addition, preserve the scalar multiplication, and preserve the zero vector. What about the subspace condition? I think it's here. Okay, subspace condition here, okay. Close under addition, close under scalar multiplication, and the zero vector, where the third condition was not really necessary because you can always plug in c equal to 0 to deduce the third condition. It is there mainly for convenience. Addition, scalar multiplication, and 0, and the third is not really necessary. Let's go back to the original notebook. Addition, scalar multiplication, zero vector, where the third is not really necessary. Do you see the parallel? Another parallel here. Those three can be reduced into a single condition here. Preserve the linear combination. Let's go back to the other notebook there, earlier notebook. Those three can be reduced into a single condition. Close under linear combination. Do you see the parallel between the two? Indeed, those aren't coincidences. So linear maps and subspaces are closely related. And here in this section, in section 1, we're going to study some subspaces defined by linear maps. Two of those examples are kernel and image. First, the kernel. The kernel of a linear map F is a set of all elements in vector space capital V that are mapped to the zero vector. The zero vector in vector space W, as a matter of fact. You see, the function value or the image vectors are all from W, so this zero vector belongs to W. But it's a bit too confusing, so let's not worry too much about that. So please note that the kernel is a subset of V because every element of kernel belongs to vector space capital V. So it's easy to see that this is a subset of V. Now, is this a subspace? Indeed, it'll turn out to be a subspace, but that's something we'll have to check in proposition 1.2. It's coming. Another subspace that we're going to be looking at closely is the image. Image of F is a set of all vectors in W which come from vector V as a function value or image, F of V. And this kind of thing used to be called a range. In college algebra and in intermediate algebra or even before, it used to be called a range. And after calculus, we used to use the term range. But here in linear algebra, we use the term image. Image versus range, in terms of the concept, they are the same thing. But we're using different terms because we have different history and different perspectives, rather. And the general element of the image looks like this. Oh, by the way, if you're comfortable with this logical expression, including the sum or if there exists quantifier here, go ahead and use it. If you're comfortable with this, W is equal to F of V, where there is a certain V inside capital V. If you're comfortable with this quantifier and how you know how to use it, then go ahead and use it. But probably not everybody is really comfortable there, because not everybody took the, what do you call, the Math 3320, I think, the Introduction to Proof course. So I'll assume not everybody is comfortable with this, so let's go ahead with this one. There's a pro and con. Pro is we don't have to deal with this quantifier, that's pro. And the con is it's a little bit less clear what subset is this. Well, the general element here, the arbitrary element, is a form of f of v, and f of v belongs to the target. You see, f is sending element of capital V to element of capital W. So the function value or the image value, f of v, belongs to W. So this is actually subset of W. It's a bit harder to see. From here, it's easier to see because, you see, W belongs to capital W. It's a little bit easier. But then again, that'll make this condition part a little bit difficult to see. If you use this expression, and the arbitrary element is a form of capital F of V, then we don't really have to consider this logical quantifier and things like those, but it's a little bit harder to see that this actually belongs to W. But remember that. I'm going to be using this expression, this notation, far more than these. Our textbook author is using this way, but I'll try not to use W. Whenever I select an arbitrary element from image, I'm going to begin with f of v so that I can avoid this kind of expression. Okay, if you're already comfortable with all or some quantifiers, then that's fine. You can go ahead and use everything you want. Okay, let's go over to the next topic. We have to prove that kernel, which is a subset of V, is a subspace. And then we have to prove that image, which is a subset of W, is actually a subspace. So let's go ahead and prove those. Kernel is a subspace. You see, I'm not using the set inclusion anymore. I'm using less than or equal to sign between sets, not between sets. When the right hand side is a vector space, then this less than or equal to sign means the subspace. So I hope everybody remembers that. We talked about those in Module 5 and that reinforced in Module 6. But since then, we haven't used those kind of notation very often. And less than or equal to symbol represent subspace. Okay, let's prove this. Okay, how do you prove that this is a subspace? Do I still have that old notebook? I closed this, so let me open it up again. So let's use these. Close on the addition, close on the scalar multiplication, and the zero vector. Okay, all right. So V1 and V2 belong to kernel, then some must belong to kernel as well. That's something we have to prove. Next, closed under scalar multiplication. V belong to kernel. C belong to the set of real numbers. Then scalar multiplication, C times V belong to kernel. That's something we have to prove. And then the third It may not be that necessary, but let's do it anyway. Does a 0 vector belong to kernel? Here, 0 vector in vector space V, to be a little bit more precise. So let's prove these three. The third is not really necessary, but let's do it anyway. It's the easiest, so let's start from here. Now, what do you mean by some vector belongs to the kernel? It must satisfy this. F of that vector has to be a 0 vector. So let's check that. F of 0 vector is equal to 0 vector. Is that true? Yes, of course. Therefore, 0 vector belong to kernel. By the way, OV and OW actually are adding confusion, so let's not use those anymore. Okay, how about the first one then? Okay, V1 and V2 belong to kernel. What does that mean? They're satisfying these, right? Kernel means the vector satisfies this, which means f of that vector is 0 vector. So what do we know? F of V1 is 0, and also f of V2 is also 0. Okay, that's what we know. And then what we want about V1 plus V2. We want to prove that this vector belongs to the kernel. So f of that vector has to be 0. That's what we have to prove. Let me repeat this. What do you mean by this vector, which I just highlighted, belong to the kernel? F of that vector has to be equal to 0. See the condition here? So that's what we want. So f of V1 plus V2 is equal to 0, 0 vector. That's what we have to prove, but it's easily proven here. You see, the linear map preserves the addition. So you can separate the addition and we get 0 plus 0 because f of V1, f of V2, both are zeros. So we get 0 plus 0 is equal to 0, and therefore V1 plus V2 belong to the kernel. So there goes the proof. The main body part is just proof by algebraic manipulation. We wanted to prove f of V1 plus V2 is equal to 0. And what property did we use? The property of the linear map, and then we ended up with 0 plus 0. So this is the main body of the problem, and this is the conclusion part. This one, the first part is not really necessary. So if you skip this one and then get only this one and the conclusion, you will get full credit. If you do only this and then did not write the conclusion, I don't like it very much, but chances I will not take off any point. It's likely that I will not take off any point, but still, it's not a good proof. You have to have conclusion. And as for this one, if you skip it, I'm not going to take off many points because it's just a repetition of this one. But still, there's no condition, there's no question that the presence of this part make this proof a little bit better, a little bit easier to understand. Let's see, shall we use the same idea to prove number 2 here? Let's go ahead and do that. So what do you mean by V belong to the kernel? F of that vector is equal to 0. That's the condition for kernel. And then C belongs to the Scala. Then we have to prove that C times V belong to kernel, which means that vector, f of that vector is equal to 0. So we're going to prove that f of is equal to 0 vector. That's what we want to prove. And you can prove it rather easily like this. It's C times f of V, and this is C times 0 vector, isn't it? F of V is 0, so it's 0 vector. Therefore, C times V belongs to the kernel. Again, the same comment. This part is the main body of the proof, and this part is the conclusion. I like to have the main body, of course, the 90% of the proof, and the conclusion. Forgetting the conclusion, I don't like it very much. You see, I would like to have the conclusion. As for this part, it's not totally necessary, but having something like this definitely make this proof better. By the way, this is not implication as a matter of fact. It's just going over to the next step. Sorry about that. That was not double arrow mark. Sorry, the previous expression was a wrong proof. Even though if you do it like that, I'm not going to take off any point. Still, and this comma is just separating this first sentence and the second sentence. And then you can use period if you prefer. But it's not logical implication, no. By the way, what did I do here? In my notebook, instead of using these three conditions, I just went over to linear combination. And let's see, V1 and V2 are in kernel, so f of V1 is 0 and f of V2 is 0, kind of like this part, yes. And then we just put everything into the linear combination, f of A1 V1 plus f of AV1 plus BV2, and then separate those linear combination, get 0, and here goes the conclusion. So I use the, where is the notebook there? Old notebook. Yes, instead of these three, in my notebook, I just used shortened version, just used this one, and provided a shorter proof here. Which proof do I prefer? The shorter proof here, as I have in my notebook, or a little bit longer version with 1, 2, 3? Personally, I prefer the longer version, these 1, 2, 3. Nonetheless, I use the short version in my notebook here, even though my preference is actually the longer version. Okay, so much for the proof of the first claim. And then the proof of the second claim, let's come back and talk about it in a separate video.